Hi, we're Team PWR Play. I'm Brian Malanka.
I'm Dylan Hole.
I'm Robert McVicker.
I'm Justin Ramsey.
And I'm David Signestad. Nuclear power provides a safe and reliable source of energy generation, with nearly 20% of the power consumed in the US being generated via nuclear means. This demand is rising due to many factors, including development of AI data centers, population and economic growth, and electrification of our daily life. Of the reactors in the US, two-thirds are pressurized water reactors, or PWRs. Building a PWR is not an easy feat, and they must be simulated and certified before even breaking ground. Existing simulations lie at one end of a spectrum. They're either too simple with no computational aspect, or they're robust commercial simulators that overwhelm a user who doesn't have years of experience. We fill in this gap with our PWR simulator. Its focus on time-dependent behavior of the reactor will give future engineers the tools needed to fulfill the rising power demand. I'll now hand it over to Robert, who will talk about how we approach this goal.
The scope of this project is to develop an educational simulator of a pressurized water reactor. The model focuses on the primary loop and includes the key subsystems, the reactor core, hot and cold legs, steam generator, and the pressurizer. The reactor core model includes point kinetics, fuel and coolant energy balances, and reactivity, which drive the system response. Each subsystem is modeled using a lumped parameter, time-dependent approach to capture how the system changes over time. From a user perspective, interaction is limited to two inputs, control rod position and steam demand, which affect reactor power, temperatures, and pressures. The model is limited to normal operating conditions and does not include accident scenarios or the full secondary system. With that scope defined, I'll hand it over to Justin to walk through the research phase.
Thank you, Robert. In this project, we modeled a pressurized water reactor based on an AP1000 design. This includes the reactor vessel where the heat is generated in the core and transferred to the coolant. We model reactor power using point kinetics, which captures how power changes over time. The reactivity effects from the control rods and temperature feedback are accounted for along with the fuel and coolant energy balance to represent how heat is transferred in the coolant. That heat is carried by the primary coolant through the loop. The hot leg carries the heated coolant from the reactor vessel to the steam generator. In the steam generator, heat is transferred from the primary side coolant to the secondary side producing steam. The coolant then returns through the cold leg from the steam generator back to the reactor vessel. The pressurizer maintains system pressure and keeps the system operating in a stable condition. Overall, this creates a dynamic model that shows how reactor power, temperature, and pressure change during operation. At this point, I'll hand it over to Brian to walk through how we actually implemented this in the simulator.
We started by evaluation of different programming language options, defined what the model needed to do, and ultimately selected Python for its flexibility and strong library support. From there, we moved into a modular design approach. We defined the overall system architecture, broke the PWR into key components, and developed each subsystem independently before integrating them into a unified simulation. During testing and integration, we established a framework to bring everything together incrementally. This allowed us to test interactions between subsystems, improve stability, and refine performance as we went. After the PWR model was complete, our focus moved towards continued refinement, expanding functionality, and completion of the graphical user interface, or GUI integration, to make the simulator more interactive and user-friendly. And with that, I'll hand it over to Dylan to walk through the user interface and how we've brought the model into an interactive environment.
Great. Thank you, Brian. Now that we have completed the programming phase, this is the graphical user interface, which is really what the entire project has been building toward. It allows us to take that model and actually interact with it in a more intuitive way. I'm going to walk through an example where we lower the control rods to reduce the amount of energy being produced in the reactor. Now we can see how the system responds on the graph on the right-hand side. From there, I can use the time slider to move through the simulation and get a more detailed look at the system outputs at different points in time. I can also use the pop-out feature to open additional graphs and look at specific parts of the system in more detail. For example, here you can see that the core temperatures decrease as the control rods are lowered. This gives us a clear view of how the system responds to different inputs and provides a way to analyze different operating scenarios. And with that, I'll move into our conclusion. With the growing demand for energy and increased interest in nuclear power, we identified the need for a more user-friendly reactor simulator to help educate people on how these systems work. We then defined and researched the key subsystems, built a simulation to model how the systems behave, and developed a graphical interface to bring the model to life. Overall, this allows users to explore how the system responds to different inputs and analyze different operating scenarios. Thank you.